ANOVA is an acronym which stands for Analysis of Variance. It's a test that we use when we want to determine whether or not a significant difference exists between 3 or more means. And in this video, we're going to talk about using ANOVA and what to do after you use ANOVA. So if you understand ANOVA, the null hypothesis is always a claim of equality, and in this particular case, the null hypothesis for ANOVA is that there is no significant difference between the means. The alternative hypothesis is that somewhere there is at least one significant difference. Now, when you run ANOVA, because ANOVA only tells you whether or not there is a difference, in other words, it tells you whether it exists or not, it doesn't tell you where it is. So when you run ANOVA, there are two possible outcomes. You can fail to reject the null, in which case the null hypothesis, which is assumed to be true as part of the process, it's not disputed. We don't accept it, but we're saying that the evidence we have does not show that there is a significant difference between the means in question. So that's one outcome. The other outcome is where you reject the null. And so the proper interpretation of that for ANOVA is that somewhere among those means there exists a significant difference, but we don't know where. And so only when you reject the null from ANOVA do you need to follow up with some kind of a post-hoc test. Now, it turns out that there's more than one post-hoc test. For us, though, there is only one because we only cover the one in our course. We cover Tukey's test. And so the purpose of Tukey's test is to locate those significant differences between the means in question. So to put it differently, what we're saying is like this. Look, if you run ANOVA and you fail to reject the null, you're done. There's nothing else to do. The conclusion would be that the evidence shows there is no significant difference among the means in question. However, if you run ANOVA and you reject the null, there is an additional step required, a post-hoc test, which again for us is Tukey's test. And the purpose of that is to find out exactly where that significant difference or significant differences are found. So you only need to run Tukey's test if you reject the null from the ANOVA process. In this video, we're going to use a prepared example that spreads out over a couple of different sections of the text. You can see the example on the screen in front of you here. And so if you'd like to follow along, feel free. You can pause the video and you can key in those data sets right there. You're going to key them into the lists from your calculator. So you can see you have 4 data sets, and that means you're going to need a total of 4 lists to hold them. In any case, let's see what the problem says. Prosthodontists specialize in the restoration of oral function, including the use of dental implants, veneers, dentures, and crowns. Since repairing chipped veneer is less costly and time-consuming than complete restoration, a researcher wanted to compare the shear bond strength of different repair kits for repairs of a chipped porcelain veneer in fixed prosthodontics. He randomly divided 20 porcelain specimens into 4 treatment groups. Group 1 specimens used Cojet, Group 2 used Silastor, Group 3 used Samara, and Group 4 used ceramic repair. At the conclusion of the study, shear bond strength in megapascals or MPAs was measured according to a particular standard, and the data was recorded in Table 1. So the first thing that they talk about there is it says verify that the requirements to perform one-way ANOVA are satisfied. Now you can read about that in the text. I'm not going to cover that in the video here. And that is part of the process. If you don't verify that the requirements are satisfied, you could be potentially creating kind of a garbage in, garbage out situation. So I'll leave you to read that. And if you're working on a different problem, which is not laid out in this fashion, of course we would do that. But we're not doing it here just for brevity's sake. So let's assume that those conditions are satisfied. And then what we want to do is we want to run ANOVA, and we want to pay attention in particular to what do we need to write down, and what do we do from the ANOVA process. In other words, do we need to use post-hoc testing or not? So feel free, pause the video if you would, and key that in, or you can just simply follow along from the text. So as you can see, I've cleared my lists preparatory to keying that in. So I'll go to the Stat menu, I'll go to the Edit submenu, and I'm going to use List 1 through List 4. Always a very good idea to keep a record of what's in what list. It will really help later with regard to the post-hoc testing, but in any case, let's key this in. And so on. Let me just accelerate this process here. So as you can see, I have all my data keyed in, and at this point I am ready to execute ANOVA, and we can then pause and see what we've got. So you want to quit this, you want to go back to the Stat menu, you want to go to the Test submenu, and then usually you can just go straight up. If you happen to remember the letter H, which designates it, or at least that's what it is on my calculator, you can just go directly to the function by using the alpha and then the letter in question. So in this case it would be alpha and then this key here. In any case, you just press enter and select it, and when you run ANOVA, the calculator wants you to tell it what lists you have your data in. So we have list 1, list 2, list 3, and list 4. And so when you run it, you get quite a bit of information out of the calculator. Now you don't need to write down all of this, but you definitely need to write down some of it. So what is the salient information here? First and foremost, we have the test statistic, and we want that to be written down because it basically showcases whether or not the data was keyed in correctly. So in other words, if you have the same test statistic that I have when I run the test, that tells me that you got everything keyed in right and that you executed the test correctly. The next thing we want to record would be the p-value. The p-value, or using the p-value rather, to decide the outcome of the test is much easier than using a rejection region. But if you insist, you can use the rejection region. I'm not going to complain as long as you have everything noted so that I can see that you did the test correctly. Now, with regard to what we see here, I'm looking at that p-value, and I can see that it is a very small p-value. It is actually less than the level of significance that's presented in the problem. So we're going to be rejecting the null. And when we reject a null, as we were saying, that means that we need a post-hoc test. So we need to run Tukey's test. So if you're working smart instead of working hard, there's a few other details you'd want to get off of this screen before you move along to execute Tukey's test. And so in order to get those, you're going to need to scroll down, and you'll notice you'll notice there's a number right here that's under the error section. It says MS equals 8.835. That is the error mean square, and that number is something you need in order to run Tukey's test. So it's very smart to get it right now before you move along. Let's take a look at what we're going to be recording from these screens here. So what you can see here is what I would typically write down for an ANOVA test, whether or not I'm going to reject, but I've added some conclusions here. So notice the null and the alternative hypothesis. That is a good kind of abbreviated way to write them both. So the null hypothesis is saying effectively that mu sub I is equal to mu sub j for I not equal to j, meaning in a technical way we're saying that none of the means differ significantly. And that's versus the alternative hypothesis, which says that mu sub I is not equal to mu sub j for some I not equal to j. So that's kind of the abbreviated way we would write that at least one of the means differs. Now you can read in the text alpha is given to be 0.05, and so I've written down my test statistic, as you can see, and I've written down my p-value, and as we said, because the p-value is less than alpha, we're going to reject the null. And so only when we reject the null do we realize, okay, there's going to be some additional testing. We have to locate specifically where that difference is at. And so for that reason, I would then jot down also the error mean square, because as you're going to see, I'm going to be needing that for Tukey's test. And so this is sufficient for the moment, but of course we have more to write. So the next thing I would typically want to have would be a record of what's in what list. You can write that before you record the hypotheses and all the rest of the stuff that we just showed, or you can write it now, whatever seems good to you. But we need to have this because, as you can see, I'm going to be recording the sample means from each of those lists, and that's something I'm going to have to obtain. In this case, it's actually given in the text, but normally you'd have to get it as part of the process. So how would we go about getting that? Well, let's take a quick look. We're going to have to come back to our calculator here, as you can see, and so we want to get out of this. I would usually just quit it, and then I can go back to the stat menu, and I'm going to be fetching those sample means. Usually I would use the one variable stats, which is this function you can see right here. You can select it from the list if you like, or you can simply press enter. And for my calculator, we have this particular interface, and so we have to tell it, what list. So you tell it list 1, the frequency list you should leave empty, and then you're ready to calculate. And so you can see right there that it's going to cough that up, and so we have x sub 1 bar is 16.28. So let's record that. You only need to record sample means to one place beyond whatever the data shows, and so in this case 16.28. And we want to get the others in a similar fashion. You can save yourself a little bit of time by recycling that command. All you have to do is press second enter, and then change the name of the list to the one that you're interested in. So in this case it would be list 2. And so you can see that the sample mean for the oscillostor is given right there, and so let's record that as well. And so on. And so you want to record each of those in that way, and once you have those, and you're ready to move on. Now once you've recorded all of these, at this point you're ready to commence with Tukey's test to locate the particular difference. Where is it at? And before we launch on Tukey's test, there's probably a few other things we want to make sure of. Now I'm assuming as you look at this video that you're also sort of looking at the text, and so you're trying to reconcile what you see on the video with what you find in the text. So understanding what we're showing here, the foundation for that is all laid out there in the textbook, and so please make sure you're reading that carefully. Now we are at this point ready to commence with Tukey's test, and the purpose again is to locate the specific differences that were identified by ANOVA. We want to find out exactly where they are between these means. And probably the first order of business with regard to Tukey's test would be to dig out the critical value. So let's take a look at that. So here you can see the notation which is used for that critical value. If I was reading it to you over the telephone, I would read it as Q sub alpha, comma V, comma K. And alpha, we know, that is the level of significance. It was given previously in the previous section as 0.05. V is a little bit tricky. It's the degrees of freedom. And so effectively it is the number of observations minus the number of means being compared. And so if you go back and look at our calculator very briefly, you can go back to the lists here and take a look. If you count them, or if you remember from reading it earlier in the problem, we have a total of 20 observations here, and we are comparing a total of 4 different means. So for this particular problem, the degrees of freedom would be 20 minus 4, otherwise known as 16. And finally, the last parameter that you need for finding this critical value is K, which again is the number of means being compared. So we know that it's 4. And so those 3 numbers, 0.05, 16, comma 4, those are the numbers we need in order to navigate the table for finding the critical value. Let's take a look. This is the portion of the table that we need here. This is table 10, as you can see. And so when you're navigating this table, there's a few things you want to pay attention to. First of all, you want to pay attention to the level of significance, which is given at the top of the table. As you can see, it says alpha is 0.05, which is what we have for this particular problem. The next thing you want to look at is the row that corresponds to the degrees of freedom. So for this case, it's row 16. And then finally, you want to find the intersection of row 16 with the column that at the top has the number of means being compared. So the value of k, if you recall, was 4. So we're looking for the intersection of the row that has 16 on the left and 4 at the top, as you can see. And so the value that I'm seeing right there is 4.046. Now, with regard to navigating this table, there is one little blurb in the text that often gets overlooked. And so we'd like to point it out to you now, and I'll probably end up pointing it out later as well. But notice carefully, if you look at that very first column on the left side there, that the values go from 19 to 20, and then it jumps to 24, and then 30, and then 40, and then 60, and then 120. So you notice that there are some gaps there. And so it begs a question. Let's say, for example, you were working on a problem where you happen to have something like 45 observations. And so which value would you be using for your degrees of freedom? Take a look. Notice it says under step 4, if the critical value were not in table 10 because of the value for V, use the entry corresponding to the value closest. So for the example that we were talking about, let's say we had 45 degrees of freedom, something like that. In that case, you go back to your table. And so here's your table, and you can see that there is no 45. So in that case, since 40 is closer to 45 than 60 is, you would use 40. And so if you had, for example, let's say 5 means you were comparing, then you'd be at column 5, and the value you'd be taking would be 4.039. In any case, let's take a look at what we're doing here, and we'll see where we're going to go next. So as you can see, I have my sample means, I have my critical value, and I have a table of sorts, which I'm going to assemble. And it's going to mirror a table you will see in the text with some minor differences. In any case, notice I have, for my table here, I have x sub 1 bar versus x sub 2 bar, x sub 1 bar versus x sub 3 bar, and so on. Sullivan follows a slightly different order when he does this. He arranges the means in a particular order, in ascending order, and then he goes on that basis. For me, I always want to make sure I don't overlook any of these comparisons. It's very easy to do. And so I start with x sub 1 bar, and I just kind of systematically work through all the others. So x sub 1 versus 2, 3, 4, and then x sub 2 versus 3, 4, and then x sub 3 versus 4. And so in that way I know that I capture all of the things that I need. And let's see what we need from the text. Now on the screen in front of you here, you can see the test statistic which is used for Tukey's test. There is a fair amount of write-up concerning this in the text, and so I would invite you to be sure to see that. It is easy to overlook. A couple of things. We want to make sure that the numerator of this test statistic is always positive. And so when I show my calculation, I just make sure to do the larger of the two means minus the smaller of the two means. If you want, you can use an absolute value function or whatever, but the bottom line is we must have the numerator positive. As far as the rest of the test statistic, you notice something called s squared in the denominator radical. And as you can read elsewhere, that is the mean square error from ANOVA. That's why we wrote it down back when we did that, because we knew if we rejected, we were going to need it for Tukey's test. So we have it. And as far as the n sub I and the n sub j, those are the sample sizes of the samples being compared. And in this particular example, each of the samples has 5 observations. So in other words, 1 over n sub I plus 1 over n sub j is going to be 1 over 5 plus 1 over 5, which is 2 over 5 for each of the comparisons. So recognizing that here can help you to kind of speed the process a little bit. Now we're going to replicate the following table, just not necessarily in the same order that you see it recorded here. So for example, Sullivan does Sillastor versus Samara first, but in our calculation we are going to do Cojet versus Silastore first. And so we're not going to record everything you see here. We're just going to record, as you saw on the screen a few seconds ago, we're going to record which of the means we're comparing. We're going to write down our test statistic, and we're going to write down our conclusion, or as it's called here in this table, our decision. So let's go to the calculator and see how it plays out. So for my test statistic, my numerator is going to be the difference of the means, and in this case my sample means are as follows. For Cojet, the sample mean was 16.28, and for Silastore it was 17.64. So Silastore is larger, and that means that in my calculation I'm going to make sure to do the larger of the two first. So that's the numerator of my test statistic, and the denominator is going to be that big radical expression. So I need to open up a couple of parentheses here, and I'm going to put in my mean square error, which was 8.835, and that does not change from one comparison to the next. And I'm going to divide that by 2, as I was told, and then I'm going to multiply that by 1 over sample 1 plus 1 over sample 2. And as we were saying, each of the samples has 5 observations. So this would be 1/5 plus 1/5, which of course is 2/5. And so with that, I've constructed my denominator, and I'm ready to get my test statistic. So 1.023, and you don't need to write it down to a huge number of places. You know, usually 3 places is sufficient. So let's do that. So my test statistic we found was 1.023. And as you can see, that value is lower or below the critical value, so I can't reject. And so what that means is that there is not a significant difference between those two means. Now, the rest of the calculations are fairly repetitive, and so I can harness the power of the calculator to speed me through that. I want to compare sample 1 with sample 3. So I'm going to regurgitate that last key sequence, because really all I have to change is the numerator. Now in this particular case, the sample means are 16.28 and 10.64. And so I want to take 16.28 minus 10.64. But the rest of the test statistic is the same. And so there is my test statistic value. Let's jot it down. And you notice that that value is larger than the critical value. So in that case, I'm going to be rejecting. And now I'm ready to compare sample 1 with sample 3. Excuse me, sample 4. So again, all I have to do is regurgitate the key sequence. And I'm going to go back and edit the numerator. So again, the mean from sample 1 was 16.28, and it is larger than the mean from sample 4, which was 10.78. So really all I have to do is change this, and there's my test statistic. Let's jot it down. Now that's also larger than the critical value, so we'll be rejecting there as well. And so on. And so you can do the rest of the comparisons in this way, and if you do, here's what you should obtain. So as you can see, I have the values there on the screen, and here are my results. So we have rejected the null in the case of sample 1 versus sample 3, sample 1 versus sample 4, sample 2 versus sample 3, and sample 2 versus sample 4. And so we want to summarize this. And for that, there's a couple of different ways to write it, but let's take a look briefly at the text. There are two different ways to report the result. And so you can see them here in step 6 on the screen in front of you. Both of these can be a little bit confusing at first. You have to be careful of the order of the means when you put this down. And so if I'm taking what we've gotten, let me show you how I would record this. So we found that sample 1 and sample 2 were basically comparable. In other words, there was no significant difference between them, and likewise between sample 3 and sample 4. But if you recall, we found that there was a significant difference between the groups. So in other words, we found that sample 2 and sample 3, and sample 2 and sample 4, and sample 1 and sample 3, and sample 1 and sample 4, they differed. And so I'm going to summarize that as follows. Now in this case, it works rather well to use equals and not equals. It doesn't always. And so there is another style that can be deployed to indicate which of the means differed and which didn't. And so we could show that here as well. We found that 1 and 2 were comparable, and 3 and 4 were comparable. And so in that way, we're suggesting the fact that they are separate and that there is a significant difference. But both of these summaries are a little bit deceptive, and if you haven't actually looked at that table, it can be easily misconstrued. And so look very carefully at this and understand that sometimes the results aren't as clear-cut as you might think. In fact, we're going to show you that in another example. So if you have any questions about this one, I hope that this video was helpful, but feel free to drop me a line and take a look at the next video.